On behalf of Olympus, I'd like to welcome all attendees to this live webinar on improving small diameter pipe weld inspections with an encoded phased array. The session will last about 40 minutes, followed by a Q&A session. You can post your questions anytime during the webinar, but they'll be answered at the end. Your presenters for today are Nick Bublitz and Mark Cart. Nick is a technical support manager at Olympus NDT of the Americas and based in Houston. Mark Cart is a business development manager for petrochemical and fabrication, also at Olympus NDT, also based in Houston. Without further ado, I'd like to hand over the microphone to Mark Cart to start the show.
Good afternoon, everyone. Just would like to go over a few of the items that we'll introduce today in a part of our presentation. We're going to focus today on small diameter piping in the industry, which opens up a huge venue of applications in the industry. We're going to review a few of those. We're going to talk about phased array from an introduction standpoint, just a briefing. The Cobra tool that we provide, we manufacture here at Olympus, and it's a very novel phased array solution specifically for small bore piping. We're also going to talk about phased array ultrasonics and compare it to radiographic inspection. We've got some real good illustrations, some radiographs, and some ultrasonic data, one-on-one type comparison. And we're going to also talk about success stories where we have got feedback from the users of our equipment out in the industry. They've applied it. We've got examples of cost savings, some really good info that you can take home with you today. And at the end of our conference, we're going to have question and answer. We're going to talk about some of these applications in the small bore or small diameter piping world. One of the first ones is in power generation and the boilers. When we look at this illustration in your upper right section of the screen, the boiler tubes are all in close proximity. Repair, construction creates an environment where numerous workers can be involved in one strategic area. Doing ultrasonic flaw detection on these welds allows you to be in close proximity without any safety hazards and gives you a real-time update of what the weld quality looks like. Welding procedures and technique can be corrected on the fly instead of seeing it at a later date or after a considerable amount of time. In the refining and chemical world, some of the typical examples are heaters, where we have crude heaters, cabin style, can style, various, all of which have numerous tubes, close proximities, close to things like support members, refractory, and of course when they're being manufactured or when they're under repair. Tight quarters, lots of personnel, no real time or room for radiation energy. Reformers is another example. Process piping, we have a world of process piping in the upstream as well as the downstream area that's very close to one another. And then finally, ethylene furnaces, known for being just literally a spaghetti bowl of tubulars inside close proximities that can be touching one another in numerous quantities. Retubes, manufacturing process, etc., again, is a very good application for close proximity, small size scanners doing well quality. And then finally, in the oil and gas production world, the offshore platforms, control systems, various types of piping and flow. We have new construction, but also on-stream quality evaluation, damage mechanism detection, and repair and replacement. Very, very close tolerance, very close proximities. Okay, now I'll turn it over to Nick.
Thanks, Mark. We've had kind of an overview of some of the typical applications and industries where we'd be targeting inspection with phased array on small diameter piping. We'll look back a little bit historically at some of the ultrasonic challenges of applying ultrasonic NDI to these welds. Typically, small diameter piping, there are many, many welds to inspect in a short period of time. For example, in a boiler, it could be a high volume, several thousand tubes. Process piping is very similar. Another limitation can be the limited space between the pipes, whether that's boiler tubes, water wall tubes, process piping. There's often very little clearance to apply NDI 360 degrees around. There might be other process piping and other obstacles around it. We typically can't move these components. They're part of a system delivering a chemical or other component. We can't move it like a vessel or move it to a safe area to perform radiography. So we're kind of fixed in a stationary area. A lot of times we have welds with limited access. We don't have access to the opposite side. Sometimes we have curvatures and other geometry in the pipes, connected pipes, U-bends, etc. to deal with. There's often a wide variety of diameters and thicknesses, materials, specifications. With conventional ultrasonics, often we're left with no written record besides a handwritten report that a level 2 shear wave operator has performed an inspection and based on his qualification found X amount of defects. So we're often left to the quality of the inspector. If we look at phased array ultrasonics, and just a brief introduction, it's basically an advanced application of ultrasonics. The conventional physics are the same as the conventional, but we use advanced software as well as multi-element arrays to basically increase the capabilities of ultrasonics. The technology goes all the way back to the medical field. If any of you have had a pregnant wife or had been pregnant yourself or went for another diagnostic, the rudimentary technology behind medical phased array is very similar to what we offer. Basically, the heart of any phased array system is a multi-element sensor. Shown here are both a 5 megahertz 16-element sensor doing a shear wave sectorial scan on the right, as well as a 5 megahertz 64-element probe doing a linear or multi-rastering 0-degree inspection. Each one of these elements inside of the transducer is individually wired to a pulsar and receiver, allowing us to do advanced control of the beam that is not possible with conventional probes and wedges. The two main things that we do with phased array transducers in the normal NDI industry is the linear electronic rastering of a single angle, either at 0 degrees or at a shear or refracted longitudinal wave angle, or as seen on the right, what's probably phased array is most popular for is the multi-angle shear wave inspection or sectorial scanning. If we look a little bit at a typical phased array display and phased array in general, we're usually looking at applying phased array either in manual or encoded mode. When we discuss encoding throughout the presentation, what we're talking about is having a small wheel or a scanning device that will record as we move the probe down the weld. This allows for a full archived digital file at the end that can be post-analyzed and saved for the life of the component or pipe. It's a small, usually 20, 30 megabytes for a small two-sided examination of a pipe, so we can store many of these without sacrificing a lot of storage capacity. The images that we create, usually in weld inspection, are a direct result from collecting all of the A-scans amplitude information and plotting it in a top-down C-scan presentation. If we look at the picture presented here, it's basically if we cut a weld of a pipe and laid that weld out flat, it's a 365-degree display of the entire weld. Allows for the permanent digital record, provides better flaw detection and analysis than conventional methods due to the multiple angle approach. We're able to pick up some flaws that might be harder to characterize conventionally or even detect, and provides for offline analysis and manipulation of data, post-processing gain levels, merging multiple files together, just a really advanced approach to ultrasonics. We'll go back a little bit and look at the physics of the two techniques that we're talking about today, radiography versus ultrasonics in general, but in particular encoded phased arrays. If we look at their ability to detect defects and their probability of detection of defects, radiography is generally known to be more sensitive to three-dimensional type discontinuities, such as slag, porosity, and lack of penetration. The phased array and ultrasonics in general are almost 180 degrees different. Their strength in detection and sensitivity is to two-dimensional discontinuities, such as cracks and lack of fusion. These type of defects are usually what we consider more critical in the strength of a fused weld joint. One of the big advantages of phased array that we see people wanting to use ultrasonics in lieu of radiography is the ability to provide not only length and defect characterization, but also the through-wall height. And we'll see in the next slide how being able to determine the height allows us to apply engineering critical assessment and not just general weld quality assessment. I guess it's another slide ahead. We'll look first at some of the additional radiography disadvantages that we can see in some inspections. Obviously, there's an inherent radiation safety hazard that's inherent with radiography use. The increased licensing and training cost, including safety training and training of workers that work around the radiography when it's employed. If we're talking about film-based radiography, often there's chemical waste, consumable costs associated, disruption of work areas, extra movement of parts in order to not disrupt other operations. Film deterioration if we're forced to store our film for a certain amount of time, as well as can be relatively a slow speed, especially as we work with thicker and thicker components, and also the additional processing of film and radiographs. So comparison image there on the side, you can see a radiograph of the same weld and the difference in the data, and we'll look at that a little further with some real-life examples later in the presentation. Further to the point, this is a chart about the difference between workmanship versus engineering critical assessment acceptance criteria. And this one's just used out of an example. I think this comes out of an ASME clause somewhere. But if we look at it, we basically have the different types of imperfections on the left, as well as standard and fracture mechanic type data. Now, this is just an example. So we're using actually it's from a 42-inch pipe and a half-inch wall, but it's very similar, thin wall. Piping. And the standard clause basically represents what reject criteria we must apply to these type of defects if we only know the length and the type of defect. On the right, under the fracture mechanics, which is synonymous with ECA or engineering critical assessment, it's basically showing us two separate columns that if we know the through-wall height of these defects, we're actually able to accept much longer lengths in some cases. So if we just take one of these as an example, we'll use the incomplete fusion buried. So here we have a weld lack of fusion probably on the bevel, and it's not ID or OD or inner or outer diameter connected, but it's somewhere in the middle of the weld. If we use the standard clause where all we can say is it's a lack of fusion, we have an amplitude value, and we know the length of it, we must reject that in this case in the 42-inch pipe, half-inch wall at 2 inches of length. Basically, we must assume the worst case in that case. Now, if we look at the fracture mechanics, now if we're able to look at that defect and our NDI provides us with information that we can assess that that flaw has a through-wall height dimension of less than about 2 millimeters or 0.075 inch, we're actually able to accept a very long run of 16.8 inches of buried incomplete fusion. Now, this is going to vary based on your acceptance code and your standard, and also in this case, the way the formula works is it's based on diameter and wall thickness. But in almost all cases, if we're able to assess that through wall height, we're able to accept longer defects. Let's look a little bit at the code acceptance of phased array because it's been a very important part of phased array in the market, and it's been especially for small diameter piping and replacement of radiography. Historically, if we take the biggest example, ASME has been the most proactive across the Americas anyway, being very supportive of the use of phased arrays. We've had a number of code cases for a number of years that can be applied. Talk about code cases, we're talking about codes that don't sit inside of the code, but they are stipulations and requirements that one can go out and apply above and beyond the referencing section and use advanced and other types of NDI. So we had several code cases for a number of years used for both manual as well as encoded phased arrays. The ones that are most particular to small diameter piping are usually B31.3, code cases 181 and 179, which is basically using ultrasonics to replace radiography in materials 1/2 inch and less, as well as the alternative acceptance criteria related to it. Last year, a big event happened in that ASME directly brought these code case type inspections directly into the body of the code. Article 4, Section 5 happened in July 2010. So if some of the same requirements where somebody used to have to apply a code case and go above and beyond normal requirements, now there's a mandatory appendix, basically Appendix 4 through 8 that addressed most of these requirements, including manual phased arrays, using electronic and sectorial scans with encoders, and also different workmanship and fracture mechanics like criteria, and also performance demonstration criteria. So these are directly referenced into mandatory appendixes as well as the still existing code cases. So we look back a little bit. What has been the limitation of some of the use of phased arrays in the early years? Well, relatively, the design and implementation of the probes has gotten much better. Phased array probes can be very, very small and very high performing today. So the engineering has improved. See in the picture some bigger arrays for weld inspection. Typically large scanners that didn't necessarily address the need for low clearance and obstacles. Flat arrays, which we'll get into a little bit, but basically common 1D linear arrays had some limitations for the unique acoustic that go inside thin wall piping. We'll look at that. The idea of ultrasonics and limited thickness, beam spread, and be able to not only detect but size accurately small defects in thin wall pipe. So we'll see how that's being addressed. Been very few service vendors for phased array. Not a lot of operators out there that were providing phased array inspection services. The cost of both the equipment and having a vendor provide it could be costly. Very few training academies and documented requirements for training in the industry. Very few operators and aggressive competition for qualified phased array operators. And then code and customer acceptance. And really on all regards, this whole list has been dramatically addressed in many ways. We'll look at some of those as we move on. So we look here first time at the Cobra solution. This is a semi-automatic scanner solution coupled with any number of phased array instruments, but we like to promote our very portable OmniScan MX and MX2. When we say semi-automatic scanner, we're talking about a operator-driven but encoded device. So in the tail of this scanner, there's a small encoder that as we rotate around the weld, we will be recording a direct linear correlation with our sound entrance into the weld along with our travel of the scanner. With that design, there's a low profile clearance of 1/2 inch or 12.7 millimeter to allow for inspection even in the closest of piping. It fits a range, a very specialized range designed only for small diameter piping of 0.84 inch to 4.5 inch outside diameter. So it's not a catch-all, it's a very specialized for small diameter piping only. We do offer other scanners that work with the accessories, the OmniScan and water pumps, etc., but this is really a specialized scanner. It's really adjustable to all materials because it's not magnet-based and rather link-based and wraps around pipe sizes. There's no limitation to the material having to be magnetic. It's highly portable. We can see here an operator has a strap around his neck. He's able to carry the OmniScan. He can carry a small water pump, and then basically just the Cobra scanner. So if we have access issues or we need to climb up into rafting, use up ladders, rope access, it's a fairly small portable system. Also for transportation from job sites, a Pelican case for the OmniScan and some spares and a Pelican case for the complete Cobra kit. It does offer for dual or single-sided access. So basically on the scanner, we're able to disconnect the scanner here in the middle if we have an elbow or a U-bend or some other limitation where we can't do dual-sided inspection. We're able to do one side of the weld with about just over a 2-inch footprint back from the toe of the weld. And then we've coupled that with specialized internally curved arrays that address some of the acoustic issues in thin wall piping, and we'll look at that in more detail as we move on. So here's the Cobra solution, and what we've done is we've tried to couple it into a complete package, so it's a very turnkey return on investment type solution for our customers. It's basically all the diameters of wedges, a pair, both flat, and then a pair of curved wedges to fit 0.84 all the way to 4.5 inches. We've got the scanner mechanism itself, all the links, all the tools. Then we've coupled it with a template system that allows you to easily set up the scanner by selecting the links that fit into the applicable template. And you can put both sides of the scanner together and then connect them through the bar if you're doing dual-sided. So very clean and neat. Adjustment of the scanner to any diameter. Can be used with a simple manual water pump, bug sprayer type, or an automatic pump. You can get very small, up to 4 liters or so. Will get you a long range of inspection time. And then it's compatible with analysis directly on the unit, or we can bring it over for post-analysis and do some advanced merging and other reporting gain adjustment that's not possible on the OmniScan and offline analysis software as well. Look a little bit at the probe and wedge detail. The wedge is a 60-degree shear wave wedge, common. We do also offer some other wedge designs on demand, but this is our standard for nominal schedule piping. All the different curvatures wedges there. The standard probe we promote is a 7.5 megahertz. We do offer both lower frequencies, which are popular for austenitic materials, as well as higher frequencies for very thin, so 10, 1.5, 2, 5 megahertz as well. We do see here that there's an irrigation system, so coupling is fed directly into the probe. Transversely, it goes through the wedge and then into onto the part to provide coupling. So there's no need to provide gel coupling. This allows us to be coupled 360 degrees around the weld. The main detail of the probe that makes it special, you can't really tell from the outside. Obviously, it's been designed for low clearance to allow for that half-inch clearance. But the other thing is, internally, we have applied a curvature to the elements to help adjust the beam spot size and the accuracy in analysis and measurement. If we look at the two examples here, a normal linear array probe that we'd use for a general application is flat in the side-to-side axis. We do have some ability to do some focusing actively to improve beam spread in the active axis, but up till the internal focus of the curvature, the mechanical curvature on the new probes, we had very little control over the beam size in the passive axis. So if you look at the comparison here with the curve, we have a much smaller spot size, which will translate in most applications into a better signal-to-noise ratio and length measurement possibility. Look at an example here, direct comparison that we did during testing of the product before releasing it. This is a 2 3/4 inch diameter pipe. We're using the general requirements of ASME B31.3 code case 181. This has an OD notch of 6.9 millimeters and also a through-wall hole. The data is going to focus. We did a 6 dB drop of the notch using both, keeping all the other variables as same as we could, same pitch, same frequency, etc. With a flat array, we can see a little bit of the distortion of the notch visualization here, as well as a 6 dB drop technique measurement of 9.6 of the 6.9 millimeter notch. Here we did the same test with the curved array. You can see a much cleaner representation of the notch in the C-scan here, and a very accurate 7.1 millimeter measurement of the 6.9 millimeter notch. So this is a typical result. The OmniScan is capable of doing several phased array scans simultaneously, but with nominal schedule small diameter piping, typically a single sector scan from each side will be enough coverage, which also results in pretty small file sizes and pretty simple analysis in most cases. Now these are separate basically scans from each side of the weld. We have our S or sector scan. We have individual A scans relating to every position of the scan. So those are archived and saved for further analysis or just to comply with raw data storage for code. But this is basically an amplitude-based C-scan. Again, so it's like we cut off the weld, laid it flat, and basically all amplitude-based colors. So if we have our reject level set, we're typically looking for the red and hot orange colors that might be reaching our reject levels based on our calibration standard. So once we find defects and start analyze them, it's typically a process. There's usually certain information we're trying to find. So we might analyze, determine whether it's a geometry signal or it's a defect, and then we're usually looking for the amplitude of the flaw to look back at our acceptance criteria and see if it's a rejectable amplitude. We'll want to know the depth from the top of the pipe as well as the through-wall height. So here we're doing a 6 dB drop through-wall height measurement. Again, that's the advantage of using ultrasonics, is getting that very easily. Here we just use a cursor and it'll give us that reading. We're able to go to the C-scan and get a length sizing, again, probably using a 6 dB drop technique and placing the cursors at those extents. And then we're able to also get things like volumetric position. So here we have an automated reading. We can also see on the image, it's kind of hard to see, but there's a center line reference that shows us where the center line of our weld is, so we can position that defect based in the index axis. And then we're basically, usually based on our ultrasonic knowledge, the operator will also make a characterization of the flaw, whether it's a slag, a crack, a lack of fusion, etc. All this can be recorded and saved in the file and also be reported in a concise HTML report. So here's a typical OmniScan report that we can spit out real time in addition to saving and archiving the file or any customized reporting. At the top, it's basically stuff about the equipment being used, the module, the mainframe unit, which software version we're running, when it was calibrated. All of our probe information here, probe and wedge, all of our setup information specific to how we've set the OmniScan up to do the inspection. We also have a little bit of calculation showing that we're doing a sector scan, what angles we're using, basically everything that we designed into our scan plan, which we'll talk about here shortly. Look a little bit further, we are able to put in some part information here, stainless steel, the fact that it was 8 millimeters thick, different scan lengths. So this is basically our encoded that shows how much we inspected and what our resolution was. In this case, we were taking data every millimeter at every angle. So every slice of the C-scan down here at the bottom is a 1 millimeter slice. And then we have what we call our defect table, which is our most common version of reporting. In this case, they reported 2 separate defects. We have a whole slew of selectable readings, but in this case, there's typically the ones we discussed before. Those are interchangeable. We can also zoom, highlight, look at different views in between flaws and represent them in various ways before we hit add to add to them to the report. So here we have flaw 1 and flaw 2 on the next page, and then we have an indication table of all flaws. And there's our second flaw, and place for it to sign. Now this is highly customizable, fully HTML compatible, so you can use an HTML editor, or you can also customize right in the software and save a template so that you don't have to redo it. You can put your company logo in the beginning of the report here versus the Olympus one, and enter user fields very easily to comply the reporting to your needs. So we'll step a little bit away from the Cobra solution itself and present a real-life test that we did here with 3 tubes comparing radiography test as well as phased array ultrasonics with the Cobra. In this case, the component under test was 3 pipes referred to as pipe 1, 2, and 3. The 44.5 millimeter diameter steel pipe. Wall thickness was actually quite thin for ultrasonics. It's a 4.5 millimeter wall thickness, and the weld configuration was a single V. We put a variety of manufactured defects into the weld. Basically, most of our most common weld defects. We see toe crack and root crack here of 6 millimeters, single porosity as well as a cluster porosity colony, a lack of sidewall fusion, as well as an incomplete penetration. Look at just a basic diagram of how the radiography would normally be performed for this inspection. If we look at, for a reference, ASME Section 8, Division 1 and 2, basically guidelines for boiler power plant constructions. It's dealt with in Appendix 4. Look for a radiography thin wall. This is a good example of how this might be performed. Usually try to do at least 2 radiographic shots 90 degrees out from each other to compass the whole weld. Usually done at a slight offset in many cases. In the case if we don't have access to take it from both sides, there's some exceptions that can be made, but typically we'd like to have at least 2 shots. Look at how we normally do this with phased array and the system that we're talking about today. It's actually a pretty simple scan plan. We talked about scan plans. They're very important with encoded ultrasonics and phased array in general. So we're going to be putting the probe in a fixed position. We're no longer going to be rastering back and forth. So we need to know basically that we have full coverage, proper incidence on our fusion lines, etc. So we almost always start with what we call a scan plan, which is choosing the correct probes, wedges, angles, position from the center line of the weld to ensure all these things. So we use an offline program. Typically we use a program called ES-Beam tool to select our probe and wedges, draw our weld in, then adjust parameters to document and tweak our coverage for the best test possible. Here, as alluded to before, very simple with thin wall. A single sector scan will give us the coverage and incidence needed to do this inspection. We're basically repeating that on both sides of the weld. In this case, we have access to do it from both sides. So after our scan plan design, we program it into the OmniScan. We'll also go and do a series of calibrations as necessary. We have wedge delay calibrations that will allow to adjust for wedge wear or any slight differences in depth measurement on the calibrated reflector that we might see between the angles due to their incidence of angle hitting the calibrated reflector. We're also able to do a sensitivity calibration, and this is a very important one that is going to make all these different beams that we're using for the inspection all equal, so they all see the number 3 or whatever notch size defect that we're trying to detect and reject all equally. So we're able to apply the same sensitivity and acceptance reject criteria no matter what beam sees the defect. And then if needed, typically not in thin wall pipes, we also have the ability very easily to go and do material attenuation compensation. It's not usually necessary in thin wall, but it can clean up signal to noise ratio if used, but also for thicker wall it can help compensate for the loss of power of the sound as it travels through very thick or very coarse-grained materials. So we have the ability to do that as well. And everything in the OmniScan is done pretty much in a wizard-type database. So in this case, we would naturally train the probes over the calibrated reflector, see how each angle sees it, both in depth for wedge delay and amplitude for sensitivity, and hit adjust, and the instrument will equalize to the tolerance that we have given. There's also a few other parameters typically set up, the start and stop. We usually go about 365 degrees around, and what resolution or at what interval we want all the data to be taken. And typically 1 millimeter is typical. If we look at our few pages of comparison scans here, we have the radiograph on the top left in each case, as well as the ultrasonic data from our offline analysis software. So it was brought from the OmniScan over into TomoView, and some merging was done to provide a very good display of the data. So here in the radiograph, we have a somewhat hard to see toe crack in contrast here, as well as a incomplete penetration that shows up pretty well in the weld zone. The bottom here, we have our toe crack representation. If we break this display down a little bit, we've built an overlay representative of the side view of the weld, and we're repeating that for the different legs of ultrasonic data, so that when we see a defect, it plots real to the position in the weld. So we have an S-scan or side view, and the other main view we're using here is a C-scan type view from each probe. Here we've overlaid the data from both probes or both sides of the weld on top of each other so that we can display it in a single view on top of the weld overlay presented. On this side, we do see the incomplete penetration very clear. Again, we're using an amplitude-based thing, so things that are bright red are reading in the 80% and greater region of our screen and coming out bright red and orange. Here we look at pipe number 2. The defects in this pipe were a root crack, which can be hard to pick up in the radiograph here, as well as a lack of site of fusion that shows up quite well in the radiograph. Here is the representation of those 2 defects in pipe 2. We have a root crack, a little bit lower sensitivity, but still very clear against the background indications. Shows up pretty well in this display here. Then we have the lack of sidewall fusion, which is as well very clear against the white background or 0 noise level. Results on pipe 3. This one had a single pore as well as the cluster porosity, which are spelled out here, the black against the white. It's a little bit dark in that region to see. But here we have the single joint porosity as well as the cluster porosity. Again, very clear in the ultrasonic data. So kind of an overview. We're able to easily detect it. We can easily we're able to see all the defects that we had in the pipe and be able to size them down to a 1 millimeter accuracy, which is very, very good detection capability and analysis capability, and able to go back in. We could go back and do a repair on those pipe if we wanted to. So kind of the findings, the basis overview of that. The advantage of phased array in this case would be able to do a very high resolution encoded scan. In this case, we did a 0.5 millimeter scan resolution, so every half millimeter we were taking a slice of data from all of our beams. Using the focused arrays, we had a very high signal-to-noise ratio, so all our defects stood out quite clearly against the nominal levels. Also used a beam sweep or angular resolution of a half-degree angle. So if we want to do through-wall height measurements, we're going to have a very precise measurement. Defect length, orientation, and depth were easily determined. Provided very fast inspection and with immediate results where we could see and start analyzing our defects immediately. Very audible in a very small digital file that can be stored on pretty much any recording medium. Data that can provide us the proper feedback for process optimization. Very environmental friendly, no hazards to doing the test. We can conduct the test right next to other production and manufacturing activities. And then we have no disruption to production. A few success stories. I'll cover a few and also hand it over to Mark at some point to discuss one of them. I'm very proud of this one. It's a military client doing replacing radiography with semiotic phased array. So doing the technique we've been discussing. They found a huge benefit in the confined spaces of the ships of being able to not stop operations, not having to work at night when operations were down, not paying overtime to work at night, and not having to have the additional workers for safety on the confined ship and confining with the military regulations. Typically when they did radiography on the ships, they'd have to have 5 to 30 men to do a single radiography weld inspection due to the close countings and the safety regulations. And they were able to reduce this to 1 or 2 persons to do phased array inspection and weld. They did 3 complete ships that were scheduled for weld inspection, the process piping on the ships, and they estimated an average of 500,000 to 1 million job per ship so far. I'll turn this one over to Mark to make a few comments.
Okay, thanks, Nick. Just as additional examples of success stories, we recently had a user of our equipment do a boiler project where they retubed boilers, and they reported somewhere between 125 and as much as 132 welds per 8-hour shift with a 2-man crew. This was real pleasing to the people who had received the contract to revamp this boiler. They finished way ahead of schedule and significantly under budget simply because they could continue welding and they were doing evaluation on the fly. So they could determine if they had bad welds, they could plan repairs accordingly, didn't have to evacuate people. Again, it complements to another boiler application. And then in the ethylene furnaces we talked about earlier, one instance was ethylene furnace that they lost feed, and the result was some pretty severe tube damage, and they had to go in and do tube repair. Again, very low clearance between the tube, especially on furnaces that have been in operation for years. They were successful in extracting tubes and replacing tubes, weld inspection at floor level and on up into the elevations in the furnace with no big difficulty from the inspection standpoint. Crude heaters, can style heaters, typically if the tubes are vertical or they're circumferentially oriented, they are close to the refractory. Extraction of these tubes, replacement, welding inside the furnace on site can be very, very difficult. There's nowhere to hide. There's no way to elute irradiation. So the ultrasonic application, again, complements the whole effort. And then now recent, the offshore piping used for control systems has experienced some SCC-type damage just from an environment, just from an exterior exposure to salt, and looking at replacing a substantial amount of small-bore stainless steel lines in a lot of the offshore production platforms. The new Bureau of Ocean Energy Management, Regulation and Enforcement is just put into law some similarities to our process safety management we've used in the refining world now for years, so we'll see a lot more opportunities out offshore. Okay, Nick?
Great, thanks, Mark. I'll look at a few more, particularly in the oil and gas refinery business. Small diameter pipe inspection using the Cobra system. This was given to us by a very good customer of ours. An example 1, inspecting 7 welds of 4-inch diameter or below. They were doing phased array in lieu of real-time digital radiography. And the estimate they gave us on this first job was that they saved approximately $5,400 per weld. So for the total of the 7 welds, they were able to save nearly $40,000. Another very close example had 6 welds in a second small shutdown type area, and they were able to do all below 4.5 inch, so the Cobra was a perfect fit, and had about $32,000 savings on the total job. A third example they gave us was before the Cobra existed. They used one of our other scanners. It's a larger diameter. I think these were about 10 or 12-inch piping, so they used what we call our chain scanner. But very similar technique, just a different scanner, still using the OmniScan. These were unique in the fact that they were stainless steel, and they were also very thick for their thickness. So radiography could take up to 10 hours per shot using a very high-energy source like cobalt. So for the entire turnaround shutdown, they estimated a savings of using phased array in lieu of radiography of almost $8 million. So a significant amount of savings. We look at the coal-fired power station. This is a recent feedback from Australia. Boiler piping, basically replacing radiography inspection again with phased array ultrasonics using the Cobra. Did approximately 8,500 welds per inspection. They've done 3 of these jobs so far, 3 of these inspections. They were very early able to detect a welding problem created at the start-stop junction, a lack of fusion that was occurring based on the way they were welding. They worked with the welders very closely to change this process because they had excellent amount of data to correlate to what was happening and where. Now there's far fewer repairs. And really their general feedback was that it worked out much quicker because they could give immediately feedback to the welder and work very closely with them to improve the welding process instead of waiting towards the next shift before the film was developed and maybe it was a different welder working. So now the net outcome was they had very few weld repairs each shift versus hundreds of weld repairs due to that immediate feedback and identification of the fusion problem at the start-stop junction. So now I appreciate you guys listening to our topics today. We're going to spend a little bit of a time going through some of the questions that have come in. I invite you, if you have additional questions, to type them into the Q&A, and we'll try to answer them as many as we can. I'm going to answer them to all the participants unless I see something of a private nature, but I think in general they look like they're open to all. One of the first question I have is, what is the minimum material thickness, example plates, and diameter for PA testing? It's a very good question. Whenever we do any type of NDI, there's a lot of variables, and those type of questions, along with the minimum defect size, it's very hard to answer a concrete answer. Typically, ultrasonics are generally accepted to be applied very well and fairly easily in carbon steel materials and aluminums in the 6 to 8 millimeter range. Beyond that, you're definitely going to want to do a lot of testing to make sure it's applicable using a reference standard and developing a test, not that it can't be applied much lower than that. We saw in the example today, we're able to apply very successfully down in the 4.5 millimeter, and in some cases, depending on the needs of the test and whether you need detection or what sizing capability, we've gone much thinner than that. So there's no real limitation beyond some of the acoustics, but it's getting pushed with some of the technology. We looked at the curved arrays and some of the things we're doing in the the higher frequencies. So not a very good textbook answer for that one, but we're definitely being very successful in the 4 even down to the 4 millimeter range. See here, with 2 probes directly opposite each other on the scan, what problems occur with, I think, crosstalk? Yep, we have another part of the question here. Can these be gated out or not experienced? Well, what's one of the main differences between phased array ultrasonics and conventional ultrasonics? Some of you guys that are well practiced in conventional ultrasonics, you know if you take 2 shear wave transducers and you face them to each other in a scanning mechanism or just with your hands, they are going to receive that signal, and you're going to get what he referred to as crosstalk or noise in the opposite channel. If we take 2 phased array probes that are programmed into the same instrument, we normally do not have a crosstalk problem. In the case of the OmniScan, they're on individual receivers through an adapter. So we have one hooked up through 1 through 64, the other one hooked up to 65 through 128 in a common configuration. And we don't normally have them on the same pulsar receiver. And also, we use a concept called focal law. So the way that we make the angles appear outside of the angle of the wedge is we apply a delay of timing to the pulsing and reception that is unique to each setup. that is able to create, say, the 35 to 70 degree beam when the wedge is a very hard 60 degrees. Now, each of those probes, when it gets data back, it's very important that your software is good, that it can sort out only the focal laws that are coming back in tune with the focal law that's sent out. So it's really the software. So when we put two phased array probes together, the data coming from the other probe is not in tune with the reflection, and basically we see little or no, under good conditions, crosstalk between them. If we do have crosstalk, it's usually due to some external noise that we can remedy in other ways. See the next question here. Do we have video of actual test? I don't have a lot of real tests. Most of our videos are on pipe standards that were manufactured. We could definitely look at making and producing videos of an actual test for that individual that posed that question. You can go to our contact us on our website and make that question, and it'll go to our salesman, and we'll follow up with seeing what we can do to provide an actual video. But we do have videos of the Cobra scanner doing tests on some generic welds, test coupons, as well as calibration standards available. What is the minimum tube diameter suitable? Can you evaluate copper tube braze joints? It's a very good question. The ability to use ultrasonics with copper tube braze joints is not out of the question. It's not a frequent as some of the other materials. Copper is unique acoustically. It's one of those that we definitely want to evaluate before we would say that it's a perfect fit or there's not some limitations in what can be done. The minimum tube diameter design of the Cobra is 0.84 inch. So below that diameter, it's not going to be a suitable fit. You might have to envision doing something different, a manual technique or getting a different wedge diameter, etc. As a question, can the techniques be transferred to very thin pipes of about 0.08 inch, wall thickness, and half-inch bore? In general, yes. Again, the whole design of the Cobra was down to 0.84 inch nominal, which is half-inch pipe generically for nominal schedule, but 0.84 actual mechanical diameter. And we've done some prove up in 3 to 4 millimeter. It's not out of the question that we could apply it again, but it's one of those ones, again, I can just caution that you'd want to do some research and have a reference standard made to see how well and what kind of information we can get at that thickness and diameter. Again, you might have to also do it mechanically, either with a small wheel encoder or manually phased array as well. There's a question here about do we have any experience gained on nuclear plants on the stainless steel that would normally be ASME? Not directly. We are re-entering the power gen market as a company. We don't have a lot of history there for the last couple of years at least. We do are working closely with EPRI as well as some other organizations in the nuclear field and 2 nuclear plant inspections. But again, my code base is typically more in the structural and petrochemical world, so I don't have any immediate feedback or certainty that I wanted to mislead you on that. So again, if you can make that inquiry directly through our contact us, it'll definitely get to us and to our technical support team. And again, you can go to our website, our contact us tab, and put in your current location in that contact us website, and we'll get somebody in contact with you. The question here about can we evaluate the similar metal connections, copper to brass or copper to steel? Currently, we have a few customers using the lower frequency, 1.5, 2 megahertz, doing some austenitic inspections. A lot of times we don't get all the full details back. I'm not sure if those what versions of stainless steel or some of those are actually dissimilar, or CRM inspections. We've worked with a handful that have had pretty good results, and I have some particular information of some austenitic and stainless. I haven't seen too much on copper. There's a military client that has currently bought some specialized refracted L-wave wedges. These are sometimes needed for austenitics and dissimilar metals. They propagate a little bit better than shear waves in some of these materials. And they're doing some evaluations, but as of to date, we have not gotten too much feedback on those particular tests as it relates to the Cobra. So we are able to produce refracted L-wave wedges. If you're going to inspect dissimilar metal connections, these might be necessary. You might also need lower frequency probes that we have produced and have made. And we're also evaluating those with EPRI and some of the other organizations in the nuclear field, but I don't have that direct feedback in where we've gotten today. Copper-nickel connections as well, copper-nickel alloys. There's some work being done there, but no hard concrete PODs done at this time. There's a question here about the shoes, referred to as the shoes of the wedges available to a circumferential scan with the Cobra probe. So normally we would call these wedges, wedges are perpendicular to the weld. They're adhered to the circumferential direction of the pipe, so we call that our AOD or actual wedges. We are able to produce what is known as a COD wedge. We're able to, say, scan a long seam versus circ weld type weld. There's some unique considerations in doing COD inspections with phased array. Because you're curving the wedge in the active plane, it does take some tweaking of the wedge files. We recommend and have a procedure that an operator is able to tweak the wedge files. It's very specific to the actual diameter because that's the active axis where the waves are being formed. So we don't recommend trying to do COD inspections without a good knowledge of the instrumentation. And even then there's some limitations in the physics and sizing capability and the higher angles in some cases. So that'd really be one you'd want to talk further to a technical representative that can fully explain some of the physics involved with COD or long seam inspection with phased array probes due to the physics of curving in the active axis. One is asking just generally any disadvantages at all. What about availability of trained technicians? That is still a problem. It's one of the things that's emerged. There's more and more. One thing I did not speak to is up to this point, at least for a long time, there was no standardized documentation of what training is required. It was kind of a generic ASME, for example, reference back to SNTC1A, but SNTC1A didn't really spell anything out in particular to phased arrays. So besides the performance demonstration that was required to show a technician and minimum requirement of being familiar with the equipment, there wasn't a lot of documented what is required. SNTC1A has published new requirements for phased array, so if that's your referencing standard for training and training of employees for NDI, they do recommend a minimum of 80 hours of phased array training on top of level 2 shear wave, I believe. That's right to a level 2 phased array, and also some recommended hours of in-field experience, on-the-job experience for that qualification. Disadvantages, it's still not a very inexpensive for many companies to buy the equipment. Even though the equipment goes down in price all the time, it's still a lot more expensive than, say, conventional manual ultrasonic equipment. Depending on what level of radiography, it's a hard comparison to make, depending on the gear and how involved. But there's all different levels. There's an ability to come in on a manual level and upgrade the OmniScan. It's an upgradable platform, so that might be an avenue. We also have the Epic 1000 from our panometric Wolfram line, which is a lower end, 12 to 15K entry into phased array. Now has limited encoding capabilities, so you can start at a lower avenue. And as your inspections and ability to get return on investment increases with phased array, move into more advanced platforms like the OmniScan and more expensive equipment after you've got a return. There is still a limit in availability of trained technicians, but a lot more today. We have several training partners. If you go to our website, you'll get a good example. There's a support under the support tab that shows our training partners, and you can see a full database of the partners that are Olympus recommended training partners for advanced and conventional methods.
We have a question about larger diameter pipe inspections. Require different wedges, inducers, transducers. Yes, the Cobra system is really designed a specialty system for small diameter piping only. It's optimized for that low clearance, the curved arrays, etc. It's not designed to be a catch-all system. But the other tools that come with it, the OmniScan, some of the adapters, the coupling pumps, obviously are adjustable. We have a whole line of different scanners that are available for different diameters. The closest one to the Cobra would be our chain scanner. It's actually applicable from 1.75 up to 38-inch piping. and that basically does not have the same clearance design and is not made to work with the optimized curved arrays, but it would be fitting for most larger diameter piping. One question about usage. Basically, the question is asking if the phased array in this type of equipment would be applicable for industrial use if it's only used 6 to 12 times per year. They're concerned about using it so infrequently that they would not have the time to be familiarized with the equipment and use it properly. It's a very good question. It has a lot of variables to it. I would say it's very specific to your need and whether or not you can make a just cause that it would be a good return on investment. One other option might be to hire out a trained inspection company to perform the service for you, and then the training requirements and the certification requirements, everything is really based on them fulfilling that requirement and you using their service to come in and do the inspections. So there might be a case for either internally learning the equipment or going out to a qualified trained service company that already exists. There's a question about transverse cracking, basically asking about transverse cracks. Technically, there is ability to modify scanners for transverse cracking, but typically all the codes allow for manual angled shear wave inspection in addition to the encoded phased array. This is typically the easiest way to address the need to scan at oblique angles to the weld to look for transverse cracking. Typically this will only take a few minutes and done, and the code allows for it. It is possible that you'll detect some transverse cracking with phased array, but normally what's done is just to do a manual shear wave scan, as well as if you need to do a lamination scan, and then do the phased array ultrasonics on top of it and document that you did the transverse requirements manually. Now, the only limitation to that is if you don't have access to 360 degrees to it, then usually you just have to document that a limited access restraint to that. Some of our customers have modified some of our equipment to address transverse cracking using conventional transducers as well as phased array, but we have not made a transverse module for this scanner as of yet. One of the good questions, and this is a very good one, can you comment on single-site access, and does this meet 100% coverage requirements? Typically what happens with single-sided access is you need to get agreement by the person you're provided service to. It's very common to list a single-site access limitation, and there's actually adjustments you can make. You might have to adjust your scan plan and a proper calibration performance demonstration block to actually show what detection capabilities are capable from one side. Phased array is a huge advantage in this versus automated or semi-automated conventional UT, because with the multiple angles, often we can show that even from a one-sided access side, we can reasonably detect defects that we could never detect prior. So the answer is not straightforward. The code allows for single-side access, but it's a burden of proof and acceptance of who you're providing the inspection for, and the person providing the inspection to agree that the single-sided performance demonstration is adequate enough. There's a question about the arrays themselves and the welds, asking are the arrays curved in the circumferential direction? Yes, they are curved from side to side. As alluded to before, we're able to focus actively in the software within physics in the front to back plane, or the active plane. We mechanically focus the arrays in the circumferential or passive axis, side to side axis, for improved length and detection, basically a smaller beam spot size. Same questioner asked, does the weld crown have to be removed? Typically not. Typically in most applications we're able to use skips into the weld with the multiple angles and get full coverage without removing the weld crown. The question about can TOF be used with a Cobra scanner? TOF is another ultrasonic technique, time-of-flight diffraction, that we often employ with phased array or by itself. It can be deployed with the Cobra scanner. We have some specialty TOF probes made. You cannot do them simultaneously due to the specialized nature of the Cobra. We had to limit the size and the clearance. So with phased array, you have a half-inch clearance between pipes using the recommended arrays. It's a little bit larger, closer to about 1 inch when we apply the TOF probes. In order to get the approximate cut angles and employ TOF correctly, we have to make a larger array, so you lose, or a larger wedge, so you lose some of the clearance. But they have to be done one at a time. So you could run a phased array scan, switch out to the TOF probes, and do a TOF scan and analyze them separately. Question about what coupling material do we use? Normally for piping, as we looked at the wedges, we had a irrigation system right directly into the probe. So we typically use water. There's usually no need where pressure piping and small diameter piping exists to use anything but straight water, and it runs directly through the wedge onto the part to make the coupling. In some cases, if you have a cold environment or something like that, you can put antifreeze or other type additives into the water. But typically, we use water because it's going to be very uniform. What you want is a very controlled pump, whether it's a manual pump or if it's an automatic water pump. You want it to be very regulated and controlled. So your valve system should be good on those types of systems. There's a question just to allude about the scanner itself, about can it be used for one-sided access? Yes, if I go back a little bit, you guys can still see my presentation. We didn't show that too well. Basically, in most of the pictures here, we have it shown with both sides of the weld. If you can see this bar in the middle picture, basically, we can take the scanner apart there, and it becomes one half of the scanner. So if we have a pipe to tube or some other configuration where we can only access one side, it's basically we would have to just do the inspection that way. So there was a better picture, and I guess we left that out of this presentation because I don't see it. But yeah, it's basically will come apart in half. About 2 to 3 inch clearance to the side of the weld from one-sided access will give us enough clearance to use the scanner by one-sided access. There's a question here generally about phased array. Is phased array a good system to inspect the wind tower welding? There's a lot of question there. We've done a lot of work with wind tower manufacturers as well as service companies. They're starting to do more and more in this industry. There's not a lot of regulations in that industry really specifying all the requirements. A lot of the towers are done using structural requirements, AWS type requirements, and we're trying to apply those, but the industry in general is a little bit behind. We have a lot of experience with the manufacturers applying encoded ultrasonics. With the manufacturing of the wind towers, phased array has been employed by some of our customers, both service companies as well as the manufacturers, but more often we use a combination of TOF and conventional UT, because in manufacturing welds of that nature, they're automated, high precision, and usually very high quality, and usually the type of defects we're looking for are lack of fusion and porosity. And based on most of the configurations I've worked with, and I've worked with installing about 8 or 9 of these systems in the manufacturers in the last couple of years, is they are easily detected with a combination of TOF and pulse echo to complement TOF to cover some of the dead zones that are incorporated with TOF. But some choose to go that route. For one, it's a less expensive route. But some have unique conditions where they want to employ phased array, or because they just want the added capabilities of phased array, they will go with phased array. The question about, I'll just read it directly. Have you had good feedback on setting the maximum sectorial angles of the Cobra probe up to 75 or 80 degrees for tube inspection of 3 or 4 millimeter? We have had some success. You'll see that this is obviously a knowledgeable question answer. Asker that has some phased array knowledge, but you'll see what we did is we're using a 60-degree wedge angle, and the purpose of that is we tried to optimize both the probes and the wedges for typical schedule small diameter piping, where our 55-degree, where we're using common applications, are usually geared for about a 32 to 72 degree sweep. The 60 degrees will allow us usually to get up a little higher and still be able to calibrate it. At that thickness and at that high of an angle, it's really going to come down to an individual inspection and proving it up. There's nothing on paper that we can say every time it's going to be great. We have had some good results and feedback from customers of doing up to 75 degrees, and a little bit farther, and either using those top angles uncalibrated and then going back as necessary if they detect something, or using them as a fully calibrated channel. But again, it's something that you're going to have to probably go through a documentation and performance to make sure with all your variables, defect size, diameter, et cetera, that you're able to perform the test.
Nicholas, Mark, I want to thank you very much. It was very informative. We hope everybody got the information they were looking for today. And once again, thanks for joining us on this Olympus webinar. And the presentation will be archived on our website at www.olympus-ims.com. And for those who could not attend, it'll be up there probably early next week. So thanks again, and we'll talk to you the next time.